Welcome to your custom deep dive. You know, we spent a lot of time on this show.
A lot of time.
Yeah, a lot of time looking at how information shapes our world. But today we are going to look at how we actually shape the information itself.
Right.
We're looking at a topic that, well, it sounds incredibly abstract at first. Navigating high-dimensional data using advanced statistics and machine learning.
It's a mouthful.
It really is. But stick with us, because by the end of this conversation, it might just change how you look at the physical world around you.
It is a profoundly important topic. I mean, we are completely drowning in data right now across almost every scientific and commercial field.
Everywhere.
Yeah, and finding the meaningful structural patterns hidden inside all that chaotic digital noise. It's arguably the central defining challenge of modern computer science.
And our source material for tackling that challenge today is a dense, highly technical, and honestly brilliant academic paper from 2020.
Oh, absolutely brilliant.
It's titled A Bayesian Fisher-EM Algorithm for Discriminative Gaussian Subspace Clustering. It was authored by Nicholas Juven, Charles Boveyron, and Pierre Latouche. And I read through the math, and I have to say,
It's heavy.
It is so heavy. But our mission today is to translate that massive mathematical framework into a clear narrative for you.
Exactly.
Whether you're a data scientist prepping for your next big project, or you're just wildly curious about how algorithms manage to, see patterns without human help, we are going to unpack it all.
We'll cover how this new algorithm works, why the older traditional methods fail so spectacularly.
And how this all culminates in a real-world application of literally cleaning up degraded photographs.
It's basically statistical magic.
It really feels like it. So let's start with the foundational problem. The paper immediately talks about the clustering dilemma. But before we get to the dilemma part, how should we define what clustering actually is in this context?
Okay, think about being handed a massive spreadsheet with millions of rows of data.
Okay, picturing a giant spreadsheet.
But, and this is the key, none of the rows have labels. You don't know what any of it represents.
Just raw numbers.
Just raw numbers. It could be customer behavior, it could be gene expressions, it could be pixels in a photograph. Your goal is to group similar observations together into a specific number of groups.
Which statisticians usually just call K, right?
Exactly, K groups. This is known as unsupervised learning.
Because there is no supervisor, no pre-existing label telling the algorithm, hey, this is a picture of a cat, or this is a fraudulent bank transaction.
Precisely. It's the exact opposite of supervised learning.
Where you feed the computer thousands of labeled pictures of cats to teach it.
Right. In unsupervised clustering, the algorithm just looks at the raw numbers and has to figure out the natural boundaries entirely on its own.
That sounds incredibly hard.
It is.
Yeah.
And the foundational tool statisticians have used for decades to try and solve this is called the Gaussian mixture model, or GMM.
GMM.
If you think back to the classic bell curve from statistics, the normal distribution, the GMM essentially imagines your data as a combination of these multidimensional bells.
Like 3D bell curves.
Yeah, you can visualize them as geometric bubbles of probability floating in space. Each cluster is a bubble.
And each of those bubbles needs to be defined mathematically by the algorithm, right?
Correct.
The algorithm has to know where to put the center of the bubble and how big or stretched out it should be.
The center point is what we call the mean. And the shape, the size, and the orientation of that bubble are defined by something called a covariance matrix.
Covariance matrix.
Right. The algorithm's entire job in a GMM is to essentially blow the perfect probability bubbles around the data point so that every single point is neatly assigned to a group.
Now, that sounds straightforward enough if we're just talking about 2 or 3 dimensions, but the paper quickly introduces a concept that completely shatters that simplicity.
The curse.
Yes. They reference something introduced way back in 1957 by a mathematician named Richard Bellman. It sounds like a curse from a fantasy novel. The curse of dimensionality.
It really does.
I'd love to explore why Bellman coined that term and why it creates such a nightmare for these clustering algorithms.
Well, it's one of the most evocative terms in mathematics for a very good reason. Bellman was working on dynamic programming and optimization problems in the 1950s, and he realized something terrifying.
What was that?
Our mathematical intuition, which is totally built for the 3D physical world we live in, it completely breaks down when we add more variables.
Okay, how so?
In our day-to-day lives, we might plot data on an X and Y axis, say height versus weight. That's 2 dimensions.
Easy to visualize.
Right. But in modern data sets, you might be looking at thousands or even tens of thousands of dimensions. Every single pixel in an image is a dimension. Every single gene in a DNA sequence is a dimension.
Oh, wow. Every unique word in a massive text document represents a new mathematical axis. Think about it like organizing your own massive library at home. If you sort your books by just 2 dimensions, let's say the author's last name on the x-axis and the publication year on the y-axis, finding a cluster of similar books is super easy.
Very easy.
All the Stephen King novels from the 1980s are right there in a neat little clump on the shelf. The space is totally manageable. But what happens when we start adding dimensions to that library?
The geometric volume of that space explodes exponentially,
yeah,
literally. Imagine dimension 3 is the exact number of pages. Dimension 4 is the precise RGB shade of red on the cover. Dimension 5 is the number of times the word "the" appears in the text.
Okay, my head is spinning already.
By the time you get to a 10,000 dimensional library, the mathematical volume is so incomprehensibly vast that the books are completely isolated from one another.
The space between them just becomes enormous.
Almost infinite, practically speaking. In high-dimensional space, almost every single point is incredibly far away from every other point. The concept of closeness or density completely evaporates.
There are no clumps anymore.
None. And this is what fundamentally breaks the Gaussian mixture model we were just talking about.
Because to draw those probability bubbles, the algorithm has to calculate that covariance matrix. It needs to estimate how every single dimension relates to every other dimension.
Yes. And the math here is brutal. The number of parameters required to define a covariance matrix grows with the square of the dimension.
The square. So if it's 10 dimensions, that's 100 parameters.
Right. So if you have a modest data set with just 100 dimensions, your matrix has roughly 5,000 parameters to estimate for every single cluster.
Just for one cluster.
Yes. If you have 1,000 dimensions, which is super common in biology or text analysis, it jumps to 500,000 parameters.
500,000 parameters to draw one bubble.
And to fit a model with 500,000 parameters accurately, you need an impractically massive amount of data. You'd need millions or billions of observations.
Which we rarely ever have. A medical study might look at 10,000 gene expressions, but they only have, 50 patients in the trial?
Exactly the problem. You have 10,000 dimensions and only 50 data points. The computer tries to draw a probability bubble, but it just collapses.
The math just gives up.
The math matrix becomes what we call singular or non-invertible. There's just too much empty space and not enough information to define the shape of the cluster. The algorithm just crashes or it spits out total garbage.
So we have this fundamental roadblock. We have massive high-dimensional data in biology, linguistics, finance, but our clustering tools choke on the sheer volume of the space.
They choke hard.
How have statisticians traditionally fought this curse before the breakthrough in this paper? It seems like the most obvious workaround would just be to shrink the library.
And that has been the standard protocol for decades. If 10,000 dimensions are too many, you find a way to mathematically squish the data down to 5 or 10 manageable dimensions.
Okay.
And then, only then, you run your clustering algorithm on that smaller, squished space. We call this unsupervised dimension reduction.
And the most famous of these techniques is principal component analysis, right? PCA.
Yes, PCA is everywhere.
I see PCA mentioned in almost every data science paper, but the authors of our source paper today argue that relying on PCA before clustering is actually a massive trap.
A fatal flaw.
I want to unpack why that is. Because it requires understanding how PCA actually decides what to keep and what to throw away when it shrinks that library. How does it make those cuts?
Well, PCA is essentially obsessed with variance.
Variance, meaning spread.
Right. It looks at the massive cloud of data points and asks, in which direction is this data spread out the most? It assumes that the widest spread equals the most important information.
Okay, that makes intuitive sense.
If you imagine your data points form a shape like a long, thin cigar floating in a room, PCA will draw its first line, the first principal component, right down the length of the cigar.
Because that's the longest dimension.
That is the axis of maximum variance. The second principal component will be drawn across the width of the cigar, and so on.
So you capture the biggest differences in the data. But where does that intuition go wrong when we're trying to actually group things?
It goes wrong because the direction of greatest variance is absolutely not guaranteed to be the direction that separates the clusters.
Oh.
In fact, they are often entirely unrelated. Think about PCA as being completely blind to the actual groups.
Because it's an unsupervised step applied before the clustering even begins.
Exactly. It doesn't know you are trying to find distinct categories. It just sees the overall global shape of the entire data set all mushed together.
I read about the simulation they highlighted from a 1983 paper by Weiqi and Chang, which perfectly illustrates this trap.
Oh, Chang simulation. It's a classic.
And I'm struggling to visualize exactly how PCA manages to literally delete the answer. Can you walk us through that 15-dimensional setup Chang created?
Sure. It is one of the most elegant takedowns of blind PCA ever published. Chang mathematically simulated a dataset with exactly 15 dimensions.
Okay, 15 dimensions.
And hidden inside that 15-dimensional space were two very distinct, perfectly separable clusters.
Two distinct groups. Got it.
Now, when you run standard PCA on this data, it hunts for variance. It finds the first principal component, the direction where the data is most spread out.
The loudest direction.
Right. That first component accounts for over 12% of the total variance in the entire data set. It is the loudest feature of the data by far.
But the catch is that massive variance has nothing to do with the two clusters, does it?
Nothing at all. It is pure mathematically generated noise. If you project the data points onto that first principal component, the two clusters overlap perfectly.
So they just look like one big, messy, inseparable blob.
Exactly. The variance is huge, but the discrimination, the ability to tell group A from group B is absolutely zero.
And where is the actual signal hiding?
The actual meaningful difference between the two clusters, the geometric gap that separates them perfectly, is hiding all the way down in the 15th principal component.
The very last one?
The last one. That axis only accounts for a microscopic 0.9% of the total variance.
Less than 1% of the overall spread. So if a data scientist applies standard PCA to this data set, trying to escape the curse of dimensionality,
they might look at the variance explained by each component and say, I'll just keep the top 3 or 4 components. That captures most of the variance, and I'll throw away the rest to save computational power.
And by doing that, they literally delete the 15th component.
They actively delete the only mathematical perspective that separates the groups. They are left feeding pure overlapping noise into their clustering algorithm.
And they will never find the true categories.
Never.
I love thinking about how this mathematical trap mirrors human psychology.
Oh, that's an interesting angle.
How often do we walk into a situation, say, a complex meeting, a heated political debate, a new relationship, and we immediately focus on the loudest or most obvious variation?
We fixate on the first principal component.
Exactly. We get distracted by the sheer volume of the argument, the flashy presentation, the most obvious demographic difference. Meanwhile, the subtle signal, the quiet 15th component that actually defines the truth of the categories, gets completely ignored.
Just because it doesn't represent the biggest, widest variance in the room, that is a brilliant analogy. Human perception is incredibly vulnerable to the PCA trap. We are often blind to the true boundaries because we're overwhelmed by the overall noise.
And that is exactly the flaw the authors are trying to fix in these algorithms, right?
Exactly. If PCA is blind to the clusters because it focuses on global variance, we need a fundamentally different method. We need a tool that actively hunts for the boundaries between groups while it reduces the dimensions not before.
And the authors call this finding the discriminative subspace.
The discriminative subspace, that's the holy grail here.
That takes us into the historical roots of the math they use. To figure out how to find this discriminative subspace without knowing the labels beforehand, they actually reach way back to 1936.
Back to Sir Ronald A. Fisher.
Yes, one of the foundational titans of modern statistics. He developed linear discriminant analysis, or LDA. And at the absolute core of that is the Fisher criterion.
The Fisher criterion.
For those of us who haven't taken advanced linear algebra recently, what is the Fisher criterion actually measuring?
It is wonderfully elegant once you strip away all the dense notation. Imagine a simple fraction. The Fisher criterion is essentially trying to maximize the value of this fraction.
Okay, a fraction. What's on top?
On the top, the numerator, you have the distance between the centers of your different groups. We call this the between-class variance.
So you want this number to be as absolutely large as possible.
Right. You want the groups to be far, far apart.
Okay, so a massive gap between the groups makes the fraction bigger. What's on the bottom?
On the bottom, the denominator, you have the spread within each individual group. We call this the within-class variance.
And you want this one to be small.
As tiny as possible. You want the points inside each group to be incredibly tightly packed together, not sprawling all over the place.
So big distance between groups, tiny spread within groups. Maximizing that ratio gives you the best possible separation.
Exactly.
I have a visual way to think about this that helps me. Imagine you are standing in a massive field, looking up at the sky, and there are two separate flocks of birds flying around.
Okay, two flocks of birds.
If you look at them from a certain angle, let's say you're looking straight up at them from below, they might completely overlap in your field of vision. It just looks like one giant, chaotic, messy flock.
Right, because you're projecting 3D space into your 2D vision.
Exactly. The overall variance is high because birds are everywhere, but the separation is 0.
From that specific angle, your between-class variance, the gap between the flocks, is essentially 0. And your within-class variance is high, so your Fisher criterion score is terrible.
But if you start walking around the perimeter of the field, changing your physical perspective, you are essentially changing the subspace onto which you're projecting that reality.
Right.
Eventually, if you walk far enough, you might find the exact angle where you suddenly see clear, uninterrupted blue sky between the two flocks.
Yes.
That visible gap means the top of the fraction, the between-class variance, is maximizing. And maybe from that specific angle, the birds in each individual flock look like they're flying in a tight, dense, overlapping formation.
Which means the bottom of the fraction, the within-class variance, is minimizing.
The Fisher criterion is basically the mathematical equivalent of continuously walking around the field until you find that one perfect golden viewing angle.
That captures the geometry perfectly. Now, the paper briefly mentions calculating scatter matrices and finding eigenvectors to do this.
Okay, let's break those down.
To keep it conversational, a scatter matrix is just a massive mathematical grid that records how every single variable spreads out in relation to every other variable.
So one matrix tracks the spread between the flocks.
Exactly, and another tracks the spread within the flocks. And an eigenvector is essentially a structural arrow pointing in a specific direction through that mathematical space. When you solve the Fisher equation, the eigenvectors it spits out are literally the arrows pointing to that perfect viewing angle you just described.
That makes total sense. Now, in a supervised setting where you already know which bird belongs to which flock, calculating those matrices and finding those arrows is just crunching the numbers.
It's trivial math for a computer.
But we are in an unsupervised setting. We don't have the labels. The algorithm doesn't know which bird is which. How does it find the perfect angle when it doesn't even know where the flocks are?
That is the incredibly difficult part. You have a massive chicken and egg problem.
You need to know the clusters to find the best viewing angle.
But you need the best viewing angle to accurately find the clusters.
It's a paradox.
To solve this, the paper builds on a precursor model from 2012, created by two of the same authors, Boveyron and Brunet. It was called the Discriminative Latent Mixture model, or DLM.
DLM. And what was the core innovation of that 2012 model? How did it try to break the chicken and egg loop?
By tying clustering and dimension reduction together into one simultaneous alternating process. It didn't do PCA first and then cluster. It did both at the exact same time.
Oh, clever.
The core assumption of the DLM is that your massive, high-dimensional space is made of two distinct things. A hidden, low-dimensional signal that contains the true clustering information, and a vast sea of high-dimensional noise that lives in the orthogonal dimensions.
Orthogonal meaning completely perpendicular. So, extending the bird analogy, the noise is just random static happening in all the directions that are at a 90-degree angle to your perfect viewing window.
Exactly. The DLM assumed that if you can just find that perfect window, the noise in the other dimensions becomes mathematically irrelevant.
How did it execute that?
It used an alternating algorithm. First, it would make a rough guess at the clusters. Then, based on that guess, it would shift the subspace angle to maximize the Fisher criterion.
Then what?
Then, from that new angle, it would refine its guess about the clusters, and it would loop back and forth.
Guess the cluster, shift the angle, refine the guess, shift the angle again.
Yes.
It sounds like a solid approach. But the authors are very upfront about the fact that DLM had a fatal flaw. They note that it had major stability issues and would frequently get trapped in what they call poor local maxima.
Right.
I want to understand why making what the paper calls hard frequentist estimates caused the algorithm to fail.
This is a classic problem in optimization. Let's use another analogy. Imagine the algorithm is trying to find the absolute highest peak in a massive, sprawling mountain range.
The highest peak.
We call that highest peak the global maximum. That's the perfect clustering solution. But the algorithm is completely blindfolded, and it's surrounded by thick fog. The only thing it can do is feel the ground directly under its feet.
So if it feels the ground sloping upward, it takes a step in that direction.
Right, and it keeps walking uphill, step by step, making absolute rigid decisions based only on the immediate slope. Eventually, it reaches a peak where every direction around it slopes downward.
And it assumes, great, I must be at the top of the world. I found the solution. It stops searching.
Exactly. But when the fog clears, it turns out it just climbed a tiny, insignificant foothill at the edge of the range. The true summit, the global maximum, is 50 miles away.
Wow.
The algorithm gets trapped on that foothill because taking a step in any direction goes down, and its rigid programming forbids it from ever walking downhill.
It refuses to go down to go back up.
Exactly. In clustering terms, this means the DLM would settle on a suboptimal, inaccurate grouping of the data and simply refuse to adjust further. The rigid frequentist approach, assuming there is one absolute correct parameter value at every step, made it too brittle to navigate complex mathematical terrain.
So if your algorithm keeps getting trapped on the foothills because it's too rigid, how do you fix it? You have to give it a better compass. You have to force it to stop relying on absolute certainty and start embracing probability and doubt. Which brings us to the absolute core breakthrough of this 2020 paper, extending the model into the Bayesian framework. They created the Bayesian Discriminative Latent Mixture, or BDLM.
The BDLM.
Let's really demystify what it means to go Bayesian in this context, because Bayesian statistics can sound intimidating.
It can, but the philosophy is a profound shift in how you treat the unknown. In classical frequentist statistics, you assume there is one true fixed physical value for a parameter, say the exact center coordinate of a cluster, and you just need to collect enough data to find it.
Like trying to find a buried treasure with an X on a map?
Right. But in Bayesian statistics, you treat the parameters themselves as uncertain, random variables that have their own probability distributions. You never say the center is exactly here.
What do you say instead?
You start with a prior belief about where it might be, and you mathematically update that belief as you observe the data.
How does that actually look inside the math of the BDLM?
Instead of the algorithm saying, I am 100% certain the center of this cluster is at coordinates XYZ, it places a Gaussian prior distribution over the latent group means.
So it uses a bell curve for its guess?
It essentially says, before I even look deeply at the data, I believe the centers of these clusters are located somewhere in this general area, distributed according to a bell curve. It bakes a layer of measured uncertainty directly into the foundation of the math.
And to control that uncertainty, they introduce a crucial hyperparameter called lambda.
Ah, lambda, yes.
I'd love to explore what lambda actually controls physically in the model space.
Lambda is the variance of that prior distribution. It acts as the dial that dictates how spread out the group means are expected to be.
So it's a spread dial.
Yes. If you set lambda very low, you are strictly constraining the algorithm. You're telling it, I strongly believe all the clusters are clumped very tightly together near the origin of the space.
And if you turn it up?
If you set lambda very high, you are giving it a very vague, relaxed prior. Essentially saying the clusters could be sprawled out anywhere across the map.
How does injecting this prior belief, this lambda parameter, actually solve the problem of getting stuck on the foothill in the fog? Why does probability make it more stable?
Because the Bayesian prior acts as an anchor or a mathematical regularizer. Remember the curse of dimensionality we talked about?
Where the space is mostly empty.
Right. In high dimensions, data is incredibly sparse.
Yeah.
When an algorithm only has a few scattered data points, classical rigid methods tend to panic.
Panic?
Yeah, mathematically speaking. They make wild, extreme, highly convoluted assumptions to try and draw a perfect boundary around those few points. This overreaction is what causes the instability and traps them in local maxima.
But the Bayesian prior prevents that panic.
Exactly. When the sparse data suggests a wild jump to a bizarre parameter value, the prior gently pulls the estimate back toward a reasonable baseline.
It says, calm down.
Basically, it says, I see the sparse data pointing that way, but my prior belief says the clusters shouldn't be that extreme. It smooths out the optimization landscape.
I see.
It essentially allows the algorithm to gracefully walk slightly downhill off the foothill because it's guided by a broader probabilistic map, enabling it to keep searching for the true global summit.
It's like having a seasoned skeptical guide with you on the mountain who says, I know the immediate slope looks like we should camp on this foothill, but based on my prior experience of the geography of mountain ranges like this, the real peak is probably further away. Let's not commit to this spot just yet.
A perfect way to visualize it. And the authors didn't just stop at creating one beautifully regularized model. To give data scientists maximum flexibility, they derived an entire family of 12 distinct submodels from the BDLM framework.
12 submodels. I found this part of the paper to be a masterclass in geometric thinking. Let's spend some time on these.
They are very cool.
There are essentially 12 different geometric lenses you can snap onto your mathematical camera to view the clusters. And they are created by mixing and matching specific assumptions about the shape and the size of those probability bubbles we talked about earlier.
The technical variations all revolve around the covariance matrix of the clusters inside the discriminative subspace. You can constrain the covariance in a few primary ways.
Okay, let's break those down. What's the first choice?
The first choice is, are the clusters spherical or ellipsoidal?
Spherical meaning like a perfect ball.
Exactly. If you assume the clusters are spherical, you are telling the model that the variance is exactly equal in all directions within that subspace. The probability bubble is a perfect symmetrical ball. This is mathematically very simple to calculate.
And ellipsoidal.
The alternative is assuming they are ellipsoidal. This means the variance can be entirely different along different axes. The bubble can be stretched out, flattened, elongated like a cigar, or squashed like a pancake.
So that's the shape variable. Then there is a second major choice, which involves the terms homoscedasticity versus heteroscedasticity. What do those dictate?
These terms govern the relationship between the clusters. A homoscedastic assumption means you are forcing every single cluster in the dataset to have the exact same volume and shape.
Like clones.
Exactly like clones. If cluster A is an ellipse stretched along the x-axis by a factor of 5, then cluster B and cluster C must also be ellipses stretched along the x-axis by a factor of 5. They are identical clones of each other, just located in different spots.
And heteroscedastic is the opposite.
Heteroscedastic is the opposite. It allows every single cluster to have its own unique, independent volume and shape. Cluster A could be a tiny, tight, perfect sphere. Cluster B could be a massive, sprawling, highly tilted ellipse. They share no geometric constraints.
So by mathematically combining these choices, spherical versus ellipsoidal, homoscedastic versus heteroscedastic, and then applying similar constraints to how they model the noise outside the subspace, they mathematically generate 12 different models.
12 distinct tools in the toolkit.
But here's the question that jumps out. Why go through the grueling work of deriving 12 different models? Why not just default to the most complex, flexible one? Why not just let every cluster be a wildly unique heteroscedastic ellipse all the time?
That touches on the most fundamental trade-off in all of machine learning.
Overfitting.
The delicate balance between flexibility and overfitting. If you use the most complex model, it has hundreds or thousands of free parameters it can adjust. It has the extreme flexibility to fit your training data perfectly.
But that's a bad thing.
It can be. Often, it fits it too perfectly. It starts contouring its massive ellipses to capture every single random outlier and piece of static noise in your specific sample, rather than learning the true underlying structural reality.
It's like a student memorizing the exact phrasing of the answers to a specific practice test without ever learning the actual subject material. They ace the practice test, but the moment you give them a real exam with slightly different questions, they fail completely.
Precisely. That is overfitting. The model is too flexible, so it memorizes noise.
Then on the other end.
On the other end of the spectrum, you have the simplest model, say, forcing every cluster to be an identical homoscedastic sphere. That model has very few parameters to estimate. It is mathematically incredibly stable. It will absolutely not overfit the noise.
But it's rigid.
Extremely rigid. If the true data actually forms long, varied ellipses, like, say, the chemical profiles in the Italian wine dataset we'll discuss later, your spherical model will underfit. It will try to force round pegs into square holes and miss the reality entirely.
So providing 12 submodels is about giving the user a toolkit to find the Goldilocks zone.
Exactly. Using model selection criteria like BIC, or Bayesian Information Criterion, a data scientist can test all 12 and find the one that is just complex enough to capture the truth, but simple enough to remain robust.
And the parameter savings here are staggering.
They really are.
For a moderately complex dataset with 100 dimensions and 4 clusters, a traditional full Gaussian mixture model requires estimating over 20,000 separate parameters.
20,000 parameters, just to define 4 groups.
Yes. But by using the BDLM framework and projecting into a low-dimensional subspace, the most complex of their 12 models requires only 325 parameters.
That is a phenomenal reduction. It completely neutralizes the curse of dimensionality by drastically shrinking the mathematical surface area.
But having this beautiful, elegant family of Bayesian models written out on a whiteboard is one thing. Building a computational engine that can actually solve it is another entirely.
A completely different beast.
Because Because calculating complex Bayesian probabilities across hundreds of dimensions sounds like something that would instantly melt a standard computer processor. How does the paper actually implement this?
This takes us inside the engine. The authors developed the Bayesian Fisher-EM algorithm, or BFM.
BFM.
It's an iterative algorithm, which means it doesn't try to solve the whole problem in one shot. It loops through a specific sequence of 3 steps over and over, refining its answer a little bit more each time until it converges on the optimal solution.
Those 3 steps being the VE step, the M step, and the F step. Let's start with the VE step, the variational E step. Because right out of the gate, the authors have to confront a massive computational brick wall. They openly state that doing true, exact Bayesian calculation for this model is mathematically intractable.
Intractable?
I want to delve into what intractable actually means at this scale.
Well, in computer science, intractable doesn't mean we don't know the math. It means the math requires so many calculations that it is physically impossible to execute in a reasonable time frame.
Impossible.
To calculate the exact Bayesian posterior probability, which means knowing the precise probability of exactly where the clusters are given the data, the computer would literally have to evaluate every single possible combination of assigning the data points to the clusters.
Every single combination. How many combinations are we talking about?
If you have $, total observations and $, clusters, the number of configurations is $to the power of dollars.
Let's put real numbers to that to feel the scale. If a data scientist is working with a tiny toy data set of just 100 data points, and they want to sort them into 4 clusters,
that means calculating 4 to the power of 100 configurations.
And 4 to the power of 100 is?
It's a number so unimaginably massive that it defies human comprehension. It's roughly 1.6 times 10 to the 60th power.
Wow.
If you took the fastest supercomputer currently existing on Earth and let it run from the moment of the Big Bang until today, it wouldn't even have made a dent in calculating that many combinations.
So exact math is entirely off the table. The universe would end before the algorithm finished step 1.
Literally.
How do statisticians work around an impossible cosmic roadblock like that?
They use a brilliant philosophical and mathematical workaround called variational inference.
Variational inference.
Instead of stubbornly trying to calculate the exact, infinitely complex probability distribution, they essentially propose a stand-in. They create a simpler, highly flexible family of probability distributions that is easy for a computer to calculate.
Okay, a stand-in.
Then, they turn the impossible calculus problem into a solvable optimization problem. They tweak and adjust the parameters of their simple stand-in distribution until it mimics the shape of the true, complex distribution as closely as mathematically possible.
I picture this like trying to draw a perfect, exact topographic map of a highly rugged, incredibly complex mountain range like the Himalayas.
Try to map every single pebble.
Exactly. Every crevasse, every jagged peak exactly is intractable. You can't do it. So instead, you take a massive, smooth, highly flexible silken sheet and you drape it over the entire mountain range.
I like this.
Then you start pulling on the corners and adjusting the tension until the sheet loosely mimics the general overarching shape of the peaks and valleys. You don't know every pebble, but you have a very workable approximation of the mountains.
That is a wonderful visualization of variational inference. And to make draping that sheet mathematically easy, the authors use a specific technique called a mean field approximation.
What does the mean field approximation actually assume?
It makes a very bold assumption for the sake of convenience. It assumes that the latent variables, specifically the assignments of the data points to the clusters and the actual center locations of those clusters, are statistically independent of each other.
Independent. But in reality, they aren't, right?
In pure reality, they aren't independent at all. But assuming they are, breaks the massive tangled equation to smaller, separate, easily solvable pieces.
So it's a necessary compromise.
Yes. So in the VE step, the algorithm uses this draped sheet to estimate the posterior probabilities. It looks at the current setup and calculates, based on my draped sheet, what is the current probability that data point A belongs to cluster 1 versus cluster 2.
Okay, so the VE step drapes the sheet and updates its best probabilistic guess about the clusters. Once it has those updated probabilities, it hands them off to the M step, the maximization step. What happens here?
In the M step, the algorithm takes those fresh probability assignments and uses them to physically update the actual parameters of the underlying mixture model.
Physically update them.
It recalculates the mixture proportions, meaning, based on the new guesses, how big is each cluster relative to the others. It updates the covariance matrices to change the shape of the bubbles. and it estimates the variance of the random noise happening outside the subspace.
The phrase used in the paper for what the M step is trying to achieve is maximizing the lower bound of the likelihood. What does that mean conversationally?
Think of the likelihood as a measure of how well your model explains the data you are seeing. You want the likelihood to be as high as possible.
Because higher likelihood means a better fit.
Right. But because of the approximations we used in the V step, we can't calculate the exact likelihood. We can only calculate a lower bound, essentially, a guaranteed worst-case scenario floor for the likelihood.
So we push the floor up.
Exactly. The M step adjusts the parameters to push that floor as high up as possible, effectively forcing the model to fit the data better and better with every loop.
So we've estimated the probabilities, and we've updated the shapes of the bubbles to push the floor up, and then we reach the F step, the Fisher step.
The heart of the engine.
This is where the angle of our view on those birds actually shifts.
Exactly. Once the VE and M steps have solidified the current best guess about the clusters and their shapes, the F step steps back and asks, given these specific clusters, what is the absolute best linear subspace to view them from?
It seeks the perfect window.
It seeks to update the projection matrix, the physical angle of our viewing window, by directly maximizing that Fisher criterion we discussed earlier, maximizing the gap between the clusters while minimizing the spread within them.
And to execute this, the algorithm uses a highly specific technique called orthonormal discriminant vectors, or ODV.
ODV.
I want to break this down, starting with the word orthonormal. Why is that constraint so important?
Orthonormal is a strict geometric rule. It means the axes of your new reduced subspace must be at perfect right angles to each other, just like the X, Y, and Z axes on a standard graph.
Right angles.
Furthermore, they must be normalized, meaning they all have a length of exactly 1.
Why do we care if they're at right angles on length 1?
Because if they aren't, the subspace will warp and distort the geometry of the data when you project it. Imagine projecting a picture onto a movie screen that is tilted at a bizarre angle. The image gets stretched and ruined.
That makes perfect sense.
The orthonormal constraint ensures that the physical distances and shapes of the data points are perfectly preserved when they're translated into the smaller dimension.
But the paper notes that maximizing the Fisher criterion while strictly enforcing that orthonormal constraint is mathematically incredibly tricky. There isn't a simple single equation you can solve to get the answer. How does the ODV technique get around that?
It uses an iterative, greedy procedure. It doesn't try to find all the axes of the subspace at once.
A greedy procedure.
First, it searches the entire high-dimensional space to find the absolute single best direction, a single line that maximizes the Fisher separation between the clusters. Once it finds that one perfect line, it locks it in and says, this is axis number 1. Then, it begins a new search for the second axis. But this time, it adds a strict rule. The new direction must be completely perpendicular to axis number 1.
So it's building a grid.
It searches for the best separation possible within that perpendicular constraint. Once it finds it, it locks it in as axis 2. Then it searches for axis 3, strictly perpendicular to 1 and 2. It repeats this greedy one-by-one process until it has built the entire d-dimensional viewing window.
I love that. It builds the perfect, mathematically undistorted viewing window, one perpendicular plank at a time.
It's incredibly methodical.
Now, there is one more piece of brilliant engineering in this engine that we skipped over. Back when we talked about going Bayesian, we highlighted the lambda hyperparameter.
The variance of the prior.
Right. The anchor preventing the algorithm from getting lost in the fog. In many algorithms, tuning a hyperparameter is a nightmare for the human user.
Oh, it absolutely is. Usually the data scientist has to guess the value of lambda up front.
Yeah.
If they guess a number that's slightly too high or too low, the algorithm crashes or gives garbage results.
And they just have to keep guessing.
They end up running the model 50 times with 50 different guesses to see what works. It's incredibly tedious.
But the BFM engine uses something called an empirical Bayes procedure. How does that save the user from the guessing game?
It's one of the most elegant features of the paper. Empirical Bayes means the algorithm essentially uses the raw data to train its own prior.
Train its own prior.
Instead of demanding a hard-coded guess from a human, the algorithm initializes with a rough estimate. Then, as it continuously loops through the V, E, M, and F steps, as it updates the clusters and shifts the subspace, it looks at the current calculated spread of the cluster means.
And it uses that spread.
It mathematically uses that spread to update the value of lambda on the fly.
It's like an old-school analog television or a self-tuning radio.
Perfect analogy.
when you turn it on, instead of you having to blindly twist the dial, trying to find the exact millimeter where the static disappears, the radio itself listens to the static, detects the faint edge of the true broadcast signal, and automatically turns its own internal dials until the music comes through crystal clear.
Yes. The BFM algorithm is actively learning how to constrain itself based on the emerging reality of the data it is processing.
That continuous self-correction creates a highly robust system. It frees the human user from tedious hyperparameter tuning and ensures the anchor is always perfectly weighted for the specific data set.
It saves so much time.
But, as any engineer knows, having a beautiful theoretical engine that self-tunes on paper is only half the battle. The real question is, how does this engine actually perform when you take it out of the pristine mathematical lab and subject it to brutal, unforgiving statistical stress tests?
That brings us to section 7 of the paper, the simulations and the benchmarks.
The authors didn't just build this algorithm and claim victory. They deliberately pitted it in a cage match against the current state-of-the-art models in the field.
They held nothing back.
They tested it against the MCFA mixture of common factor analyzers, the PGMM parsimonious Gaussian mixture models, and the HDDC high-dimensional data clustering. And they ran 2 very specific, very punishing simulations. I want to unpack both of them, starting with the dimensionality test. What exactly were they measuring here?
This test was designed to explicitly measure resilience to the curse of dimensionality. They wanted to see exactly when the competitors would break.
So they stressed it to the limit?
They simulated a data set containing 3 distinct clusters. The trick was, the true, meaningful mathematical signal separating these 3 clusters existed in exactly 2 dimensions. It was fundamentally a 2D problem, hidden inside a much larger space.
And to simulate the curse, they just started dumping garbage dimensions on top of it, pure, uncorrelated, random noise?
Exactly. They started gently. They created a 5-dimensional space, 2 real dimensions containing the signal, and 3 dimensions of pure garbage noise.
Okay, 5 dimensions.
They ran all the algorithms and recorded the accuracy. Then, they turned the dial up. They added 10 more garbage dimensions, bringing the total to 15. Then they ran it at 25 dimensions, 35 dimensions, all the way up in increments to 155 dimensions.
155 dimensions.
So by the final round, the algorithms were frantically searching for a 2-dimensional needle hidden inside a 153-dimensional haystack of pure digital static.
To score the algorithms, they used a metric called the Adjusted Rand Index, or ARI. How should we interpret an ARI score?
ARI is the gold standard for measuring clustering accuracy against a known truth. It scales from 0 to 1. An ARI of exactly 1.0 means the algorithm achieved perfect recovery. It grouped every single data point perfectly, matching the hidden truth without a single error.
And a 0?
An ARI of 0.0 means the algorithm completely failed. Its grouping is mathematically no better than a human randomly flipping a coin or rolling a die to assign data points to clusters.
So we have the arena set. The dimensions are increasing. What happens is they crank the dial from 5 up to 155 dimensions. The line graph, published in the paper, is basically a bloodbath for the traditional methods.
It is a stark visual representation of algorithmic collapse. At 5 dimensions, all the competing models, MCFA, PGMM, HDDC, they all start off reasonably well. They're clustered near the top of the graph. They can handle 3 dimensions of noise.
But the
moment the dimensionality crosses the threshold of 15 dimensions, a catastrophic failure occurs. The lines for MCFA and PGMM plummet rapidly straight down towards 0.
Why do they die so suddenly at 15 dimensions?
Because models like MCFA and PGMM fundamentally rely on tracking global variance to reduce dimensions. When you have 2 dimensions of signal and 13 dimensions of random noise, the sheer accumulated volume of variance in the noise begins to mathematically outweigh the variance of the true signal.
The static gets louder than the music.
The algorithms get completely distracted. They start fitting their elaborate covariance matrices to the random static, losing track of the 2-dimensional truth. By 25 dimensions, their ARI scores are hovering near 0. They are effectively flipping coins.
But the line on the graph for the new BFM algorithm, it's surreal. The line is perfectly, completely flat.
Yes. BFM maintains a flawless recovery score, an ARI of exactly 1.0, perfect clustering.
Unbelievable.
It hit 1.0 at 5 dimensions, it hit 1.0 at 15 dimensions, it hit 1.0 at 85 dimensions, and it held perfect accuracy all the way across the board to the maximum of 155 dimensions. It completely and utterly ignored the 153 dimensions of garbage noise and maintained a perfect lock on the discriminative subspace.
That is incredible. It proves the theoretical claim flawlessly. The combination of the Fisher step actively hunting for separation rather than global variance, combined with the Bayesian prior anchoring the model against the sparse noise, it makes it functionally immune to that specific type of dimensional explosion.
It is a definitive result. So it survived the dimensionality test, but then they threw a second, arguably harder simulation at it, the noise test, the SNR test.
SNR stands for signal to noise ratio. How did they set this test up differently?
In the first test, they added noisy dimensions. In the SNR test, they kept the number of dimensions locked at a massive 150 dimensions. But this time, they started cranking up the sheer volume, the mathematical intensity of the noise inside those dimensions.
Intensity.
They measured this intensity in decibels, the exact same way audio engineers measure sound.
Let's translate decibels into how the algorithm hears the data.
A high decibel SNR, say 15 dB, means the true signal is loud and distinct and the background static is very quiet. It's an easy problem.
And as it drops?
As the decibels drop towards 0, the static gets louder and louder. At exactly 0 decibels, the mathematical variance of the true signal and the variance of the random noise are perfectly equal. The static is exactly as loud as the music.
And negative numbers.
Below 0 decibels into negative numbers, the noise is actually objectively louder than the signal.
So as they started dropping the SNR from a comfortable 15 decibels down towards 0, essentially turning up the static in the room, what happened to the competitors?
We saw a similar pattern of early failure. Even at reasonable SNR levels, where the signal was still mathematically much stronger than the noise, models like MCFA and PGMM saw their accuracy start to degrade quickly.
Because of their reliance on global variance.
Right. It makes them highly sensitive to even moderate increases in background static.
And BFM?
BFM held strong. It maintained near perfect accuracy as the static got louder and louder. Crucially, even at exactly 0 dB, where the noise was mathematically equal to the signal, BFM reliably found the clusters and separated the groups.
It's the equivalent of being able to sit in a crowded, echoing, incredibly noisy restaurant and perfectly isolate and understand a quiet whisper from across the table.
It is. It isolates the discriminative frequency. Now, to be scientifically rigorous and fair, below 0 dB, when they push the noise to be definitively louder than the signal, all the methods, including BFM, eventually failed and dropped towards 0.
Well, of course, mathematics has limits.
If a signal is entirely and completely drowned out by chaos, no algorithm in the universe can find it. But the test proved that BFM pushed that breaking point significantly further than anything else currently available.
So those are the artificial simulations. They prove the engine works in a sterile lab. But the authors also took BFM out into the wild and tested it on classic real-world datasets that machine learning researchers use globally as standard benchmarks.
Yes, it's vital to test on real messy data. They started with some historically famous easy ones. Fisher's Iris dataset, which dates back to the 1930s. It's a simple 4-dimensional data set of physical flower measurements.
And the Italian wine data set,
which has 27 dimensions detailing the precise chemical composition of 3 different types of wine.
And looking at the tables, BFM did very well on those, but honestly, so did the competitors. MCFA and PGMM handled those relatively simple problems fine.
Right. When the dimensions are low and the clusters are fairly obvious, most modern algorithms will succeed. But then the authors brought in the heavy hitters to really expose the differences.
The satellite data set,
which is 36 dimensions based on multispectral imaging of the Earth's surface from space, attempting to automatically classify different soil and crop types.
Yeah.
And then the ultimate traditional challenge, the USPS digits dataset.
I love the history of the USPS dataset. It's a massive collection of handwritten digits physically scanned from U.S. postal envelopes. They took these messy human-written numbers and normalized them into 16 by 16 pixel grayscale images.
16 by 16.
Because 16 times 16 is 256, every single image of a handwritten number is treated mathematically as a 256-dimensional data point. Each individual pixel is an axis.
Exactly.
And for this benchmark, they specifically tasked the unsupervised algorithms with distinguishing between the handwritten numbers 3, 5, and 8.
Which, if you think about the geometry of handwriting, are notoriously the hardest digits for a computer to tell apart. They're all composed of similar Corley loops. A hastily scroll of 3 can easily look like an 8 missing a side, or a 5 with a curved top.
In a 256-dimensional space of blurry human handwriting, how did the algorithms perform when asked to separate the 3s, 5s, and 8s without any labels?
The traditional models struggled immensely. The HDDC model achieved an ARI of only 0.35. The NCFA got 0.28. The The PGMM managed to 0.38.
That's pretty low.
They fundamentally failed to find the subtle structural differences between a sloppy 3 and a sloppy 8 hidden in that 256-dimensional pixel space.
And BFM?
BFM achieved a score of 0.76. It didn't just beat the competitors, it massively outperformed them, essentially doubling their accuracy.
And if we tie it back to the math, why did it win so decisively? Because it wasn't just blindly looking at the overall variance of the gray pixels, which is largely similar across all three numbers.
Yeah.
It used the Fisher criterion to actively search for the highly specific subspace, the exact unique combination of pixels that maximally discriminated between the shapes. It mathematically found the exact curves that matter and completely ignored the pixels that don't.
Exactly. It found the discriminative viewing angle for handwriting. But recognizing digits, while impressive and historically important, is a classic, almost cliché machine learning trope.
Yeah, everyone does digits.
What really elevates this paper from a solid statistical contribution to a profound piece of applied science is the final application they present. They took BFM entirely out of the realm of abstract classification spreadsheets, and they applied it to a deeply fascinating visceral visual problem.
Fixing broken images.
Yes.
This brings us to the final act. Seeing the math, the application of unsupervised single-image denoising. When I read this section, it genuinely blew my mind. We are so used to algorithms just categorizing things. Is this a cat or a dog? Is this a 3 or an 8? But here, they are using the abstract clustering math we just spent an hour dissecting to actually reconstruct physical reality.
It is a beautiful, tangible application of the theory. Image denoising is the highly complex process of taking a photograph that has been heavily degraded by random visual static.
Like a grainy photo.
Right. This happens all the time. Maybe the photo was taken in extremely low light, or with a degraded digital sensor, or transmitted over a noisy channel.
The goal is to mathematically remove that random static without accidentally blurring or erasing the actual physical objects in the photo.
And they don't just feed the whole image into the algorithm at once. They use a technique called patch-based denoising. I want to carefully explain how the algorithm actually looks at the photograph to process it.
Right. It doesn't look at the macro picture. It breaks the entire degraded image down into thousands of tiny, overlapping square grids, which we call patches. In the experiments detailed in the paper, they use patches of 10 by 10 pixels.
So if a patch is 10 by 10 pixels and 10 times 10 is 100, that means every single tiny square of the image is treated as a 100-dimensional data point.
A single standard-size photograph is suddenly transformed into a massive data set of hundreds of thousands of 100-dimensional points.
Precisely. And the fundamental underlying assumption of patch-based denoising is a brilliant observation about the physical world. In any natural image, there's massive redundancy.
Redundancy.
There are many patches that look fundamentally identical. You have a picture of a brick wall, there are thousands of 10 by 10 patches that just look like horizontal gray mortar lines. If you have a picture of a clear sky, there are thousands of patches that are just flat blue.
So what is the BFM algorithm trying to do with this massive sea of 100-dimensional patches?
It uses unsupervised clustering. Just like we discussed with the numbers or the biology data, it tries to search the 100-dimensional space and group all the fundamentally similar patches together.
Okay, grouping patches.
It finds all the thousands of mortar line patches scattered across the image and clusters them tightly into a single Gaussian probability bubble in that 100-dimensional subspace.
And once it successfully clusters all the mortar patches together, how does that actually remove the static?
It's pure statistical magic.
Yeah.
Once they are clustered, the math allows you to essentially average them all out.
Coverage them.
Because the true physical structure, the horizontal mortar line, is consistent and identical across every single patch in that cluster. But the digital noise, the static corrupting the image, is entirely random. It's mathematically uncorrelated.
Oh, I see.
So when you average 1,000 noisy patches together, the true structure reinforces itself while the random static mathematically cancels itself out to zero. It leaves behind only the pure, true, clean structure.
And then the final step is simply stitching all those newly cleaned up averaged patches back together to form the final restored image.
Yes.
So logically, the better your algorithm is at finding the correct clusters in that 100-dimensional space, the sharper and cleaner your final image will look. The authors tested this theory on 3 specific, highly challenging benchmark images famous in the image processing world.
The Alley, Barbara, and Simpson images.
Right. One is called Alley, which is a photograph of a narrow European stone street featuring highly textured brick walls and incredibly detailed cobblestone pavement. Another is Barbara, a famous test image featuring a woman wearing a scarf covered in very complex, tight, high-frequency stripes. She's sitting behind a table with a patterned checkered cloth. And the third is a simpler image called Simpson.
The specific challenge with images like Allie and Barbara is high-frequency physical structure. The actual physical reality of the scene, the rough, granular texture of the bricks, the tight repeating lines of the scarf, looks an awful lot like random high-frequency noise to a simple algorithm.
It's a massive variance problem.
Exactly.
Right. So what happens when data scientists run traditional state-of-the-art denoising algorithms like NL-Bayes or SPLE on the highly textured Allie image?
Those algorithms are very aggressive and very good at removing noise. If you look at the flat, low variance areas of the resulting image, like a plain wall or the sky, it becomes perfectly smooth and clean. But because those algorithms fundamentally struggle to perfectly separate the complex structural variance of the physical world from the random variance of the noise, they end up smoothing over the real objects too.
They throw the baby out with the bathwater.
Exactly. The sharp defining lines of the bricks get blurred into a soft gradient. The intricate texture of the cobblestone street turns to indistinct mush. The restored image looks artificial, like it was painted over with a thick, heavy brush.
And there's one highly specific detail in the Allie image that serves as the ultimate unforgiving test for these algorithms. Up near the top of the photo, in the bright, mostly flat sky between the two stone buildings, there are a few very thin, dark electric cables running horizontally across the gap.
Yes, the cables. They are barely a few pixels thick.
When the traditional methods NL-Bayes and SPLE tried to remove the heavy noise from that patch of sky, they aggressively completely erase the cables. The cables just vanish into the blur. Because a thin, dark line across a 10 by 10 patch represents a tiny amount of variance, the algorithms can't distinguish the physical reality of the wire from a random streak of static.
They just average it away.
But I looked at the visual results in the paper. What happens when they use BFM to cluster those exact same patches?
The visual difference is striking and immediate. BFM reconstructs the image with an incredible, unparalleled level of detail. The texture of the bricks remains sharp and defined. The cobblestones look like distinct stones, not melted mush.
And the cables.
And if you look up at the top of the image, at the sky between the buildings, those thin, dark electrical cables are perfectly preserved. They run crisp and clear right across the cleaned up sky.
This begs the ultimate question, why? Why is BFM so dramatically better at the specific, highly nuanced visual task than algorithms custom-built for images?
If we pull together every mathematical thread we've discussed over the last hour, the answer is clear. It's because BFM actively hunts for the discriminative subspace.
Not just variance.
Right. When it looked at the 100-dimensional space of those sky patches, it doesn't just calculate overall variance, which would fatally blend the subtle wire and the loud static together. It uses the Fisher criterion to hunt for the exact mathematical angle that perfectly cleanly separates a cluster of sky patches containing a faint wire from a cluster of sky patches containing pure random noise.
It fundamentally finds the 15th principal component of the photograph. It locates the quiet, subtle 0.9% signal that defines the reality of the wire, even when that wire is completely drowning in the deafening variance of the static.
Exactly. Because it can mathematically isolate that specific discriminative difference using the orthonormal vectors, it can cleanly average out the Gaussian noise without ever touching or blurring the high-frequency structural details. The authors demonstrate that BFM achieves peak signal-to-noise ratios, or PSNRs, that are completely on par with or even better than those dedicated image processing algorithms.
Oh, let's hear the numbers.
For example, on the Allie image with a heavy noise corruption level, the traditional NL-Bayes hit a PSNR of 27.43, and the SPLE algorithm hit 26.92.
And where did the BFM algorithm land?
BFM hit 27.16. So mathematically, the raw numbers are highly competitive. But the qualitative visual result, the human experience of seeing the preservation of those specific wires, the sharp cracks in the pavement, the weave of the scarf, proves something profound.
It really does.
It proves that this abstract, intimidating, high-dimensional Bayesian math isn't just theory confined to a whiteboard. It is a functional lens that literally clarifies our view of the physical world. It mathematically separates the signal of reality from the static of the universe.
What an incredible journey this paper has taken us on. Let's pull all these threads together for a final summary. We started in the daunting mathematical nightmare of the curse of dimensionality, where volume explodes exponentially and data points get lost in the void of high-dimensional libraries. We explored how the traditional crutch, PCA, is often a fatal trap that actively deletes the very answer we are looking for because it's blinded by the loudest, most obvious variance in the room.
From there, we trace the elegant theoretical solution, reaching back almost a century to Fisher's 1936 criterion to actively hunt for the discriminative subspace, that perfect golden angle where the groups clearly separate. And we unpacked how going Bayesian, with the BDLM model, introducing that lambda prior distribution, provided the crucial anchor the algorithm needed to stop it from getting endlessly lost in the fog of local maxima.
We looked under the hood at the sheer mechanics of the BFM engine. We talked about how it uses the mean field approximation of variational inference to drape a mathematical sheet over impossible, intractable cosmic calculus. We saw how it builds the viewing window one perpendicular plank at a time using orthonormal vectors, and how it brilliantly self-tunes its own lambda dial like a smart radio.
A self-tuning radio.
We watched it survive 155 dimensions of pure garbage noise in the stress test without breaking a sweat, crushing the older models. And finally, we watched it magically clear up a blurry photograph, rescuing the rough texture of a brick wall and a whisper-thin electrical wire from a sea of digital static.
It is a remarkable, cohesive synthesis of deep statistical theory and highly practical algorithmic design. It proves that by forcing our algorithms to ask the right mathematical questions, by programming them to ask what specifically discriminates these groups, instead of lazily asking what varies the most overall, we can extract profound, actionable clarity from overwhelming, chaotic complexity.
And this brings me to why you, listening right now, should care deeply about this, even if you never code a line of machine learning in your life. We are all, every single day, swimming in our own high-dimensional data. We are constantly bombarded by noise, by conflicting opinions, by endless, overwhelming streams of information on every screen we look at. It is incredibly, dangerously easy to fall into the trap of PCA in our own daily lives, to instinctively focus on the loudest variance, the biggest, most aggressive argument, the most obvious, flashing trend, while completely missing the quiet, subtle 15th component signal that actually defines the truth of a situation.
Building the right mental algorithms. Cultivating the ability to pause, step back, and actively look for the discriminative subspace of a complex real-world problem, to deliberately separate the signal from the static, is a crucial survival skill in the information age. We all need to practice walking around the perimeter of the field until we can see the clear blue sky between the flocks of birds, rather than just staring blankly at the chaotic, noisy swarm.
I couldn't agree more. And I want to leave you with one final lingering thought to mull over as we wrap up. We've spent the last hour marveling at how powerful this specific Bayesian algorithm is at finding hidden, meaningful patterns without any human labels to guide it. It can blindly find the subtle structural difference between a handwritten 3 and an 8. It can find an invisible wire in a noisy sky. But what happens when we inevitably unleash these advanced, unsupervised Bayesian algorithms on massive datasets of human data?
That's a big question.
If an algorithm can uncover the perfect hidden dimensions to separate distinct clusters from pure noise without any prior labels or human bias telling it what to look for, what hidden patterns, what totally unexpected clusters of human behavior or mass psychology or complex societal trends might these algorithms find if we let them loose on the dimensions of our lives we've historically ignored? What if the true differences or the true similarities between us aren't found in the obvious first principle component of our politics or our demographics, but are actually hiding deep in the quiet 15th component of our shared daily habits?
That is a fascinating and frankly somewhat daunting horizon to look toward. The algorithms are built, they are mathematically sound, and they are ready. It's entirely up to us to decide where we point those mathematical lenses.
It is indeed. Thank you so much for taking this deep plunge into the math and the theory with us today. Until next time, keep looking for the signal hidden in the noise.